This is Dr. Carroll, and this is a video about minimum spanning trees. I hope you've already checked out my video on spanning trees. So let's talk about minimum spanning trees. So what is a minimum spanning tree for a graph with a set of vertices V and a set of edges E? Well, it's a tree, so it's a T sub M with the same vertices, but a E prime, where E prime is a subset of E, and our graph V with E prime is a connected graph. Furthermore, it minimizes the weight of T sub M such that if you sum up all of the edges that belong in T sub M with all their weights, we're going to minimize that. So an MST, a minimum spanning tree, is a minimum weight spanning tree. We're optimizing for the weight, not number of connections, but the weight. There are two major algorithms for calculating a minimum spanning tree. They are Prim's and Kruskal's. I'm going to start with Prim's. Prim's was published by Prim in 1957. It was also published earlier in 1930 by V. Jarnik. And so intuitive, or as an overview, what it is we're going to iteratively add the lowest cost edge that adds a vertex that's not already part of our minimum spanning tree. Let me show you some pseudocode to solidify this. If we had a Prim's minimum spanning tree, we're giving it a graph and a vertex. The first thing we're going to do is create an empty graph, and we'll call that GMST. We're going to add in V as our starting vertex to GMST. And then we're going to keep going through while we have unvisited vertices in G. So this is assuming that we typically want to use a connected graph such that we'll include them all. So while we have unvisited vertices in G, we're going to find the lowest cost edge, WU, from a visited vertex W to an unvisited vertex U. So of all of the vertices branching out from our tree, our minimum spanning tree, to the rest of the vertices, we're going to pick the smallest weight. And so then we're going to mark that one as visited. We're going to add that edge to our GMST. And then we're going to update all the neighbors of U in terms of their edge costs, and to include that in our searching when we're looking for the least cost edge. Now, when you hear least cost edge, what data structure could efficiently implement that? I'm hoping you're thinking minimum priority queue, a min heap, or maybe even a Fibonacci heap. The runtime for Prim's algorithm really depends on what implementation we choose for our min priority queue. So let's go through and talk about each of these components and how they contribute. So going through this part by part, creating an empty graph is going to be order 1. Adding a vertex to a graph going to be order 1. To go through all the unvisited vertices, we're going to have order of V iterations. Keep that in mind. Now, to find the least cost edge, we could do that with log V if we were using a min heap. And so to mark it one as visited would be order 1. To add an edge is going to be order 1. And then to update all our neighbors, over all the iterations, we're going to end up having on the order of E times order of log V to update all of those. And so we get overall runtime of V log V plus E log V. And so let's simplify this a little bit. We can say it's on the order of E log V because we know that we're assuming that G is connected, and therefore the size of E is at least as large as the size of V minus 1. We can do even better than this. We can get it to order E plus V times log V if we're using Fibonacci heaps. So what category of algorithm is Prim's? It's greedy. It's greedy. It goes for the lowest cost edge. It looks at all of the options on how to get from our minimum spanning tree to other vertices, and it's just going to pick the lowest edge and move forward. And that provides for a very efficient algorithm. Now, let's talk about Kruskal's algorithm. This was published by Kruskal in 1956, actually the year before Prim's was published. And what I want you to remember about this is it adds the lowest cost edge that connects a previously unconnected component. Backing up, Prim's is going to expand the tree one with the lowest cost edge. Kruskal's is going to look at all of the components and add in the one that connects, makes a new connection, but it's the lowest cost. Again, let's look at some code, some pseudocode to wrap our heads around this. Given a graph G with weights W, notice we're not starting with a vertex, then we're going to initialize our graph that's minimum spanning tree with the vertices, and then but with no edges. And then for each vertex in the graph, what we're going to do is call make set here and make a set out of each of the vertices. And then we're going to sort all the edges in the original graph by the weights. And then we're going to go through each of the edges in sorted order. And then for each edge, we're going to look and see what set it's in and see, is it not the same set as the other one? Are they already connected? Are they already part of the same set? Or are they in different sets? And then if they are in different sets, so they're in different sets or graphs or trees, as you can think about it, we're going to add that edge to our graph. And so then we need to combine those two sets with a union. So here, the runtime really depends on our chosen implementation for our disjoint set data structure. How are we going to implement the make set, find set, and union? So I'm going to assume that we're using a disjoint set forest with union by rank and path compression heuristics. So let's go through each of these components, each of these parts here. To create a new graph where we could be order 1 or order V, depending on how we implement that. And then for each of the vertices in the vertex set, we're going to have to go through them all. And then each one is going to take some time to make a set. And so we're going to end up with all of these disjoint set operations collectively taking time alpha of V. So where alpha is a very slowly growing function. So look, if you want to read up more about that, you can read in Introduction to Algorithms, section 19.4. So then sorting, using a comparison-based sorting is going to be E times log E. And then we're going to go through each edge. And so that's on order E. And the operations in that for loop, the find set and the unions, those are all going to add, they're going to take alpha of V. And so there we go as the runtime. Now let's talk about this more. So we have order v times order alpha times v, and we can simplify that further to be order e times alpha of v. Based on what we've talked about before, and we can even simplify alpha of v. Since it's a very slow growing function, we can say it's on the order of log v, and then we could even say log e here because g is connected, and so we know that e is larger than v minus 1. And so then we have overall we have an algorithm of order e log e, or we could say e log v, because we know that the set of e is less than the set of v squared. You could think of an adjacency matrix. You don't have more edges than v squared. We know that. What kind of algorithm is Kruskal's? It's a greedy algorithm as well. I hope you enjoyed that video. Check out my other videos.